Hi, my name is Nate Gearin. I'm joining you tonight from Berlin, Germany. So I've actually already done all of the recording for all of my demonstrations, and it turns out my presentation is a little too long. So I am going to cut out the introduction and go directly towards what's unique in my operating system. And if you have any questions, I'll be around at the end. I hope you enjoy it. So maybe it makes sense for me to start with the parts of my operating system that may be different from other people in our class's operating system. Uh, this is specifically the things I did for the term project, the semaphores, the mutual exclusion locks, and the pipes. So I chose to do the semaphores and locks specifically because I found them interesting problems, and I thought it was very clever how these structures were put together, sort of cool, and secondly, it didn't strike me as a very good solution to protecting resources by disabling interrupts. The problem with disabling interrupts, from my point of view, is that it's challenging to me, at least, to know if certain parts of my code are going to run quicker than a millisecond. And if I'm trying to keep a clock that has a millisecond accuracy, if I'm disabling interrupts, for example, around my memory allocation algorithm, and it happens to take longer than 2 milliseconds, then I've just missed a tick. And that is bad. So I wanted to think about if I could use locks around shared resources to protect them. Now, the way I implemented locks was, since we have a single processor and only one process is ever running at a time, I put a lock, for example, around the memory, and if a process is descheduled when it has access to a lock that protects the memory, and then the next process tries to access that memory, what's going to happen is that process is immediately going to yield. There's nothing it can do to get access to that memory. So it yields immediately with the hope that the next time the first process is scheduled, it's going to release it, and the second time it's around, it'll be able to gain access to that. So a couple things that I found were that it's sort of hard to manage global state with locks by themselves, but it's even more challenging when we take into account the fact that we've got things that are running on different interrupt priority levels. So the way I dealt with that was by actually splitting up global data structures where I could by priority level. So I have two memory pools. I have a process memory pool, which users get access to through my malloc and my free. And then I also have a kernel memory pool that is not protected by a lock, with the assumption that it's never going to be interrupted, that the system accesses through calls called kmalloc and kfree. And one of the main learnings that I had from this was that, to the extent possible in interrupt routines, we should never access global state. It just makes the solutions to these types of problems easier. So what types of shared resources do we have in our system? Well, the most obvious is our heap memory. But there are also other global variables. Like, I have a lot of doubly linked lists. I have queues that are in my operating systems. For example, the file system is a doubly linked list. We also have things in our operating system that might be interesting in the future to use semaphores for, like the UART input. Wouldn't it be neat if something was trying to read from the UART if it just went to sleep and it was never put into a ready state unless there was actually a character for it to read, and then the CPU could be scheduling processes that had something useful to do. So at this time I'm going to show you a couple of the commands that I made that can help illustrate these these data structures. Okay, so I want to show you a couple of the commands in my operating system. The first thing I'm going to show you is memory map, just to demonstrate how there are two different pools of memory. So this is just my user pool, where there are 44 blocks allocated, and here's my kernel pool. There are a lot more in there. Most of them were allocated on operating system startup. The processes are allocated in the kernel pool too. So there's also the ability to just print out stats, which is sort of nice because this is a lot of data output. So let's take a look at the locks that are in the operating system. There are 3 now. None of them are currently locked. I'm going to show you a demo here where it spins up 16 processes, and then each process tries to gain access to one lock, which means that as soon as they all try, when they fail, they will go to sleep, and they will try again in the next quantum to access that lock, at which time hopefully the lock has been released, and if not, they'll go back to sleep. If they can grab it, they will. So the number on the left is the PID, and you can see that only one of them is able to grab the lock at any time, even though at the beginning they all tried to grab it. Only number 2 was able to initially grab it, and when it unlocked it, then number 3 was able to get it, etc. So now I'm going to show you a demo where I spin up 6 processes, and all these processes do is they run in the background and they try to access the malloc data structures. Good. So I'm going to use my process listing command ps to take a look at what processes are running. Processes 2 through 6 are these basically useless processes that just block the memory data structure. You can see the operating system still running, so my malloc data structure is safe. I'm going to kill these off now. The operating system is actually slow. Well, the shell is actually slowed down by the fact that there are all of these processes accessing the malloc data structures. So now I'm going to go over to the hardware. So this is the hardware side of the program that spins up 16 processes, where each process tries to gain access to a mutual exclusion lock. The lights will now light up based on the zero-based index of the process that was able to get the lock, which allows it to sort of count from 0 to 15 in binary. Here it goes. So each time a lock goes on, a light goes on, a new process was able to gain the lock, and it's done. So you might be wondering how I'm able to guarantee exclusive access or atomic reads and writes to a lock, for example. And in the ARM Cortex-M4 processor, it comes down to 2 assembly language instructions: the load register exclusive instruction and the store register exclusive instruction. So I'll quickly explain what they are and then show you how part of a semaphore function that I wrote works. When the first instruction, load register exclusive, loads the value of a memory address into a register, and then when you want to write to that memory address, you then give the instruction 2 registers a place to put whether or not the write was successful, atomic, the value you want to write in the success register, the argument 1, and then the address to write to. And so the way it works is that if anything else wrote to that memory address in between your load register exclusive and store register exclusive, the success register would be false, and then you need to go back and try again. So this is how I implemented part of the down in the semaphore. So this first line is me loading the value of a semaphore into register 1. I compare it to 0 in line 2. Then I say if it is 0, then the calling process should just go to sleep. When something else wakes it up, it's going to return here to this next line, which is going to subtract 1 from the value of the semaphore, and then it's going to try to store it exclusively. And if it's not, if R2, the return value of the store exclusive instruction, is not 0, then it needs to go try to do it again because it means it did not get exclusive access to the semaphore. Lastly, I want to demonstrate an interesting application of semaphores, and that is pipes. So my pipes in my operating system are just like any other device in the operating system, and I made them that way so that I could use all the standard device-independent I/O calls on them. There's both a programming level API as well as a shell level API to using pipes. So when you want to create a pipe, you call the pipe create function, you pass it a path that you want to create the pipe at, and you tell it how many bytes you want the pipe to have as its buffer. And then you can call my fgetC, my fputC, and then when you want to delete the pipe, you have to call unlink. So the pipe is just a demonstration of the classic producer-consumer problem. So what we're now looking at is my shell processing commands. And so prior to pipes, my shell only processed one command at a time. And now I needed to update my shell to be able to parse out multiple commands and understand the shell of pipe. And then run all of them and hook up the standard out of each previous command with the standard in of the next command. So you can see here that I'm looping through all of my commands, and I say that if there's a pipe in between them, I create a pipe, and then I remap the standard out of the first command to the pipe, and I remap the standard in of the second command also to the pipe. Then I execute each of the processes, which means it puts it in ready state, and the scheduler will pick it up to run it at the next convenient time. And finally, I wait for each of the processes to run. When they have each completed, I delete the pipe by calling my unlink. So the program I'm going to show you is quite simple. The first thing process 1 does is it just reads from standard in here. It's called the pipe out program. It reads from standard in. As long as it's not control D, it puts it to its standard out, which is actually the pipe, and then it continues to read. The second program that I'm going to pipe to converts all lowercase ASCII characters in between A and Z to their uppercase equivalents. So let's go ahead and run it. Okay. So the first program is called read, and then I'm going to pipe it to a program called upper, which are those two programs we saw. So it's running. I'm going to hit the letter G, and it outputs a big G. Now, you have to trust me, I'm not pressing a capital G, but I'm not. Here's a P, O. Now, it doesn't do anything with numbers, so as you can see, it's working. Now I'm going to hit Control D, and the programs are over. The pipe is closed. There is no pipe in my operating system. So that's all I've got to show. Thank you for your time and attention, and I'm here to answer any questions you might have about my operating system.